Welcome to the class of Microwave and Radar Engineering. This is lecture number 1, and in this lecture we will discuss about the history of microwaves and we will discuss the introduction to microwaves. Okay. I am Mr. Himanshu Nagpal, Assistant Professor in EC Department of AKGE Ghaziabad. So first, the first is Introduction to Electromagnetic Spectrum. So this term was first introduced in the 17th century when the range of colors observed when white light is passed through a prism, in which we got the 7 different colors when the white light is passed from the prism. Now it is applied to any signal that can be decomposed into frequency components. Clear? Now next term is the electromagnetic spectrum. Electromagnetic spectrum ranges, it defines the ranges of all possible frequencies of EM radiation, means electromagnetic radiations. It extends from low frequency to higher frequency and up to the gamma radiations, means it ranges from megahertz or kilohertz to exahertz, terahertz, terahertz. Clear? And even up to the gamma rays. Now see, this one is the electromagnetic spectrum, in which you will see that this shows the wavelength and this shows your frequency. Clear? Now you will see here that as the frequency increases, the wavelength of the light of the signal get decreases, and initially when the wavelength is very high, 10 to the power 5, and the frequency is 3 into 10 to the power 8, that is of very low frequency, and the low frequency is of 3 into 10 to the power 4. This one is medium frequency, high frequency, VHF, UHF, and your SHF. Very high frequency, ultra high frequency. Clear? Now this one SHF, EHF, FIR, MIR, NIR, VL, and UV. These are the mainly concentrate for the electromagnetic spectrum, and these are also the comes under the electromagnetic spectrum. The first term, microwave, it ranges from what? Having a wavelength ranges from 1 meter to 1 centimeter, or in frequency range it ranges from 300 megahertz to 30 gigahertz. Above 30 gigahertz, this frequency wavelength becomes of the order of millimeter. Above the frequency range of 30 gigahertz, you will see that the wavelength becomes in the millimeter range, and that type of wavelength, that type of signals are known as, that's why it is known as the millimeter waves, and that millimeter waves ranges from 30 gigahertz to 300 gigahertz. Clear? Now see, the term microwave, the term micro defines what? It stands for the extremely small in scale, and it includes both microwave and millimeter wave spectrum. Means microwave is the what? Combination of microwave and the millimeter wave spectrum, that is UHF, SHF, and EHF. This one, UHF, VHF, UHF, SHF, and EHF. These defines the total microwave spectrum, and this one is the microwave, and this one shows the millimeter range. Clear? Now these are the frequency band designations and frequency bands. These are the frequency band. These are the applications. These applications in the range of this frequency bands. Like say, if I say the frequency ranges from 3 kilohertz to 30 kilohertz, and that is known as what? Very low frequency. And in the very low frequency, for the navigation purpose and for the sonar purpose, I always use this band 3 kilohertz to 30 kilohertz. Now the next one is the low frequency, which ranges from 30 kilohertz to 300 kilohertz, and application is what? Radio and your navigation. And this navigation can be divided into two types. This may be comes for the civilian purpose and it can be for the military purpose. Clear? Now next one is the 300 kilohertz to 3 megahertz, and this one is known as the medium frequency range, and which is used, application in this range is the AM broadcasting and the Coast Guard communication. Means it is used for the also for the communication for the in the Navy side. Clear? Or you can say communication in the defense purpose. Clear? Now next one is the 3 megahertz. Next frequency ranges from 3 megahertz to 30 megahertz, and it is known as the high frequency range, and the applications are 3 megahertz to 30 megahertz. You will see the applications are what? Telephone, telegraph, fax machine, ship to coast or ship to aircraft communication, that can be used for the communication, aircraft communication, or you can say it can be used for the civilian purposes or for the defense purpose. Clear? Radio and the citizens band means normal you can use if you want to communicate, you can use this band also for the citizens band. Clear? Next one ranges from 30 megahertz to 300 megahertz, and this ranges from, this is known as the very high frequency, which is having application of air traffic control, means walkie talkie. We are using in airports, we are having a walkie talkie, and for in that type of communication this band is used, 30 megahertz to 300 megahertz. Air traffic control, police, television, FM also comes under the this range. Clear? As you know that the FM ranges from what? 88 megahertz to 108, 88 megahertz to 108 megahertz. Clear? Now this can also be used for the navigational aids. Now next, the frequency term is the 300 megahertz to 3 gigahertz, and this one is known as the ultra high frequency. And in this 300 megahertz to 3 gigahertz, the applications are for the satellite communication, surveillance, television, and the for the navigational purposes. Now next one is the 3 gigahertz to 30 gigahertz, which is very important band, and this is known as the super high frequency, and this band is mainly used for the radar communication, microwave communication. As you know that this is one of the best possible range for the microwave communication, mobile communication, the satellite communication. You will see that in this range also you will see that mobile communication will be there, 4G, 5G, that comes under the range of 3 gigahertz to 30 gigahertz. Now next one is the 30 gigahertz to 300 gigahertz, and that frequency band is known as the extreme high frequency. This band is generally used for the radar purpose, and that is used for the defense applications. Clear? Now next one is the next band is 300 gigahertz to 60 terahertz, that is the far infrared region, and this region is known for the spectroscopy and the terahertz imaging. Now next one is the 6 terahertz to 100 terahertz, that is mid infrared, which is used in the guided missile and the thermal imaging when we taking this thermal imaging from the satellite. Now next band is the 100 terahertz to 400 terahertz, that is near infrared, and this frequency range have a application of fiber optical communication, or you can say this fiber optical communication can also be further used for the, can be said as a long distance communication. And this one is the visible light communication, that is 400 terahertz to 750 terahertz, that is ranges from visible light. And this is also have an application in the visible light communication, or you can say that is a optical communication. Clear? Next one is the 750 terahertz to 1 petahertz, that is a near ultraviolet. And this one is the application is optical sensors, solid state lighting, medical imaging of cells. Clear? In the medical research, medical imaging of cells, in this we use this band. Clear? Now next one is the 1 petahertz to 30 petahertz, that is the extreme ultraviolet rays, and this one having application of barcode protein analysis for the medical purposes, DNA sequences. This one is also for the medical research in the medical field. Research in medical field. Clear? Now next one is the 30 petahertz to 3 exahertz, that is known as the soft X-ray, and this one is also having application in the medical field, that is X-ray cholesterography, medical imaging of bones, airport security, border control, and the astronomy. Clear? Now means for the extraterrestrial activities we use this band 30 petahertz to 3 exahertz. Now next one is the 3 exahertz to 30 exahertz, that is known as the hard X-ray, and this one is used in the also for the medical purposes. That's why we are going towards the higher frequency. You will see that this having a very high effect on the body also. That's why we always do not prefer to have a CT scan or X-ray every day, not to have a CT scan X-ray. Clear? And this one is having an application, that is spectroscopy, scanning of microbes, and radiotherapy. These are also having a in the field of medical purposes. Clear? Now the next microwave frequency bands, and these frequency bands are standard frequency band. First one is the ultra high frequency, that is UHF, which is ranges from 0.3 to 1, that is known as the 300 megahertz to 1 gigahertz. Clear? Next one is known as the L band, that is ranges from 1 to 2 gigahertz. S band ranges from 2 to 4 gigahertz. You will see that 1 to 2, 2 to 4, 4 to 8, 8 to 12, that is LSCX. LSCX, and this band is we generally used for the educational purposes. You will see that in the college there is a microwave test bench, and that band we generally use for the educational purposes also. And you will see that the number of kids you will see in the microwave lab, that setup is always in the range of for the design for the X band. Clear? Next one is the KU band, that is ranges from 12 to 18 gigahertz. K band ranges from 18 to 27 gigahertz. Ka band, that is ranges from 27 to 40 gigahertz. Next one is the V band, that is ranges from 40 to 75 gigahertz. W ranges from 75 to 110 gigahertz. Millimeter waves, which starts from the 30 gigahertz to 300 gigahertz. As I have already told you that millimeter range starts from 30 gigahertz to 300 gigahertz. Clear? Now next one is the sub-millimeter wave, in which the wavelength becomes even smaller than the millimeter wavelength of the wave even smaller than the millimeter, that is ranges from 300 to 3000 gigahertz. Now we will see the history of the microwave. The term microwave mainly referred to the electromagnetic wave with the wavelength ranging from what? Ranging from 1 meter to 1 millimeter. Means wavelength ranges from 1 meter to 1 millimeter. That comes under the microwave band. Clear? The microwave was first introduced by the scientist Nello Carrara to designate the electromagnetic waves having a wavelength smaller than the 30 centimeter, and this one first introduced in the 1932. And the wavelength smaller than 30 centimeter means that the frequency above the 1 gigahertz. Now next one is the foundation of electromagnetic theory is what mainly defined by what? Defined by James Clerk Maxwell. Means on the this scientist developed the this scientist mainly founder of what? Maxwell's equation, in which he had laid the foundation of electromagnetic waves, basic foundation of for the electromagnetic waves, and this was done in the 1873. Clear? Now Maxwell's formulation was cast in its modern form by the Oliver Heaviside, which is having in the range of 1887. The next, this scientist Oliver Heaviside introduced the vector notation and provided a foundation for the practical application of the guided wave and the transmission lines. Means the first foundation, he has modified some Maxwell's equation also and introduced the vector notation and provided a foundation for the propagation of waves, propagation of guided waves and the propagation of waves through a transmission lines. Now during this period 18 to 87, the German physicist known as the Heinrich Hertz first provided the experimental validation of the Maxwell's theory of electromagnetic waves. Means he has demonstrated the experimental theory of what? Maxwell's equation. Means experimental validation of Maxwell's theory of electromagnetic waves. Clear? Now due to the lack of reliable microwave components and microwave sources, the growth of radio technology emerged in 1900, that is in the range of 3 to 30 megahertz and 30 to 300 megahertz. Means due to the lack of microwave sources, we generally switched into the radio waves, that is 3 to 30 megahertz and 30 to 300 megahertz, and above 300 megahertz, we will get the microwaves. And due to the lack of microwave sources, or you can say some research is going on, but in that era, radio band was extremely explored, that is in the range of 3 to 30 megahertz and the 30 to 300 megahertz. Now during the first antenna was developed by the Marconi's, that is during the 1895, Marconi experimented with the microwave communication system that worked at a wavelength of 10 inches corresponding to a frequency of 1.18 gigahertz, that is known as the L band. Means he has first demonstrated the antenna which is of the range of having a range of 1.18 gigahertz with the center frequency of 1.818 gigahertz. Clear? Marconi mainly experimented the propagation of wave about a distance of 200 2 kilometer. Clear? So Marconi's early experiments on radio, that is 1894 to 1896, were at a range of what, 1000 megahertz, that is 1 gigahertz, which is major effect in the developing a commercial wireless services. Now next one, in the 1930s, now in the late of 1930s, there will be a generation of microwave sources. Means now we will get the so how can we generate the microwave signal? There will be generation of the microwave signal. Clear? Now in the late 1930s, it became evident that several effects limit the operation of vacuum tubes in the microwave frequencies band, and the wavelength become the dimension comparable to the dimension of tube. You will see that in the 1930s, you will see that the wavelength becomes in the range of centimeter, and that wavelength of signal, microwave signal, becomes comparable to the what? Wavelength becomes comparable to the dimensions of the components, or you can say vacuum tube. So when this dimensions become comparable to the vacuum tubes, this is that's why we move to this is a major challenge for generation of microwave signals. Clear? The possibility of microwave generation is done by the utilizing a transit time of effect of the together with the lumped tuned network, which was suggested by the now in 1939, the scientists discovered the theory of the velocity modulation. Now in the same year, the klystron amplifier were discovered, which uses the velocity modulation, and due to this klystron amplifiers are the mainly for the microwave generation, and for the microwave generation this technique was used, that is known as the velocity modulation. Clear? Now in early 1940s, scientists have also invented a magnetron, which uses this invented magnetron, which is also used for the microwave generation. Means microwave source, generation of microwave source are the klystron amplifier and the magnetron. And in 1944, the scientist Kampfner also invented a helix type TWT, traveling wave tube. This is also one of the technique or instrument, you can say, for generation of microwave signal. Means magnetron, klystron amplifier and the helix type TWT. These are all the microwave generation techniques, or you can say equipments. Clear? Now the next one is the radar, the first major application for the microwave technology, and this one mainly used or developed during the World War II. During the World War II, the radar was developed, and which is the major application of microwave signal. Clear? Now see the characteristic features of the microwave signal. First we will see the limitations. First limitation, up to around a frequency of 1 gigahertz, you will see the most circuits are designed and constructed using a lumped parameter circuit components. Means if I say below 1 gigahertz, below 1 gigahertz, the lumped circuit network, lumped circuit elements, components were used. Clear? But as we move towards the higher band of microwave signal, that is above 1 gigahertz, the wavelength becomes comparable to the dimension of the, or you can say length of the component. The wavelength of signal becomes comparable to the length of the component, which results in what? Which, due to which we cannot use the lumped circuit components. Clear? So above 1 gigahertz, the propagation time of the signal becomes comparable, means propagation time means of the signal, means you can say with becomes comparable with the time period of the signal. The lumped parameter component also becomes comparable to the wavelength. This results in the rapid amplitude and phase variation of the signal with distance. Means it can say, if I say this one is the transmission line, if I say the wavelength becomes smaller, that comes in the range of centimeter or even smaller than the centimeter. Clear? So the wavelength becomes smaller, therefore the amplitude of the signal and the phase of the signal becomes variable with the distance. Means if I say at this time amplitude becomes, if I say this is a transmission line, if I want to observe the voltage at this point, you will see the voltage at this point is different, and at this point is voltage different, at this point is voltage is different, at this point is voltage is different, and phase also varies. Means this result in a rapid amplitude of phase variation of the signal with distance with the difference. Clear? So the phase difference cannot be negotiable above 1 gigahertz. Below 1 gigahertz we can ignore the phase difference, but above 1 gigahertz we cannot ignore the phase difference. Clear? So as a result, I cannot at high frequency I cannot use the KCL and KVL, and normal voltage current concept cannot be applicable at high frequency. So at high frequency we always use the concept of field theory. Means Maxwell's equation theory will be used for at high frequencies. Clear? So what type of theory was used? That is the distributed circuit theory. Distributed circuit theory states that the, let's say this one is a transmission line. In this transmission line, this one is, let's say this one is position z equal to 0. This one is having a length L at z equal to 1, z equal to 2, similarly z equal to L. Let's see, if I say this is a, so at this point the voltage and the current is different, at this point voltage and current will be different, and at this point voltage and current will be different, because the input signal having a frequency of above 1 gigahertz, and when the frequency of signal is above 1 gigahertz, the wavelength becomes comparable to the dimension of the or length of the component. Clear? So that's why we use that distributed circuit theory, and in this distributed circuit theory, their small transmission line sections are defined over a infinitesimal length. Means we will define the small sections Clear? Means we will divide the whole transmission line into the smaller sections. So at high frequency, distributed circuit is more accurate than the lumped circuit. Clear? So the use of infinitesimal means smaller elements. This whole length is divided into small components. So the use of infinitesimal is in distributed circuit require the application of calculus rather than the linear algebra. Clear? Application of calculus means integral, differential. Clear? Now challenges for in designing a microwave sources. So due to the very smaller wavelength of the signal at microwave frequencies, the transit time of the carrier through ordinary low frequency triode transistor becomes comparable with the time period of the wave, which restricts its operation at the high frequency. So therefore a new principal operation was used, that is known as the velocity modulation, which this is the one of the technique for generation of microwave signal. Clear? A number of operations were defined in the microwave signal. The operations are known as the quantum mechanical tunneling, avalanche breakdown, transfer electron techniques. These are techniques which are used for generation of microwave signal. So due to the what are the challenges in measurement? So due to the high frequency, or you can say due to the low wavelength, which is having a wavelength in the range of centimeter. Clear? So the normal multimeters which were used at low frequency cannot be used for the high wave signals. High wave frequency, I means microwave signals. So at microwave signals, voltage and current cannot be measured with the multimeter or any other low frequency circuit. Clear? So at microwave signals, the wavelength or the cables will be different. Because why it will be different? Because at that time the impedance of the parasitic elements of the microwave signals, measurement cables and connectors becomes large and frequently crosses the component value. Means the capacitance effect, inductance effect plays a major role in the at microwave frequency. That's why we cannot use the normal multimeter or normal cables. So therefore we have to develop a special cable and connectors are required for this one. So meter impedance, the meter impedance and capacitance also affect its measurement. Means cable, meter impedance, meter capacitance and the cable parasitic capacitance affects the measurement. Clear? So the most common method to do the micro measurement is to measure the field amplitude. We always measure the field amplitude, phase difference and the power carried by the waves. So these are the components which we always measure for the microwave signal: field amplitudes, phase difference and the power carried by the waves. Clear? Another term we always used in the microwave signals, for the measurement microwave signal, is the standing wave pattern measurement. So what are the advantages of microwave? First is high bandwidth. As the frequency is very high and the wavelength is very low, the bandwidth is very high. This one is having an improved gain and the directive property. Means the signal propagates in the particular direction, not having a wide spectrum, means wide area. Clear? Clear? Now having a directive properties, means it directed in a one particular direction. Clear? Next one is the reduction in antenna size. As the wavelength reduces, the reduction antenna size get also reduced, because the antenna size is generally comparable to the lambda by 4. As wavelength reduces, the antenna size will also reduce. Low power requirement, there will be requirement of very less power. Transparency property of microwave means it can also penetrate the wall. It can penetrate the wall glass. That's why we are able to get the communication through cell phone inside the room. What are the disadvantages of microwave? First one is line of sight communication. Due to its directive property, we can always use the line of sight communication. Means we cannot use the propagation where line of sight is will be not there. Line of sight means transmitter and the receiver must be in the same line. Clear? Subject to electromagnetic interference, microwave signals can be subjected to a electromagnetic interference. Microwave signals can be affected by the bad weather. Clear? Next one is the costly equipments. Next, you will see also that the microwave signals cannot be reflected by the ionosphere. This cannot be reflected by the ionosphere. That's why this microwave signals for propagation we always use the line of sight communication. Means transmitter and receiver should be in the same line, or we always have a long distance transmission. For long distance transmission, if I want to use the microwave signal, we need to have a satellite in space, so that satellite can receive the signal from the microwave and it can transmit into at another point. Clear? What are the applications? Applications are radio detection and ranging, terrestrial microwave link, transmission of many television signals over one link, satellite communication, radio astronomy, linear particle accelerator, studies on the basic property of materials, microwave ovens, industry, medical science. You will see, you have already seen that these are all the applications of the microwaves. Thank you.